And then we've got HBr. So hydrogen is acting like a metal in these single replacement reactions. So we're going to find it on the same activity series with the metals. All right, when we look those up there, find PT, find H. All right, which one's higher on the activity series, PT or H? H, or H, we're finding H is kind of in the middle. PT's really, really down pretty low. So if the single element, which is PT, if the single element is lower, Broadfoot, what did we say happens here with the single element is lower? No reaction, yeah, so we'll just say NR there. All right, let's check out the next one. The next one we've got hydrogen, so that's our single element, even though it's not a metal. We've got the hydrogen, and we've got copper. All right, compare those two. Which one's higher this time? Ainsley, hydrogen, or copper? Which one's higher? Hydrogen. Okay, so since hydrogen is higher, we need to have a reaction here. So that means hydrogen is going to take the place of copper there. I'm going to take it over to this side. I'll leave a little blank. I'm going to say H. H gets with the Cl. Oh, we made hydrochloric acid. Remember, I'll put AQ after my compound. All right, and then what's going to be left over, Jonathan? Copper, you got it. Just CU there. And then I'll put solid for that one. Then I'll balance the whole thing. Maybe a 2 there, we'll do that. Again, one of the things we're going to be really focusing on today is following the oxidation numbers of every single element, not just, we're used to trying to figure out copper's charge because it's a transition metal, but in a case like this, we're going to start following everything. And we're going to learn this. It's on the back of the sheet. One of the important rules to know is if it's a single element that's not charged, it's got an oxidation number of 0. If it's part of an ionic compound, its oxidation number is its charge, and we've got lots of practice doing that. Chloride we know is -1 because it's in group 17. Copper is +2. So it's a lot of the same things we've done for those ionic compounds. Then on the other side, hydrogen's +1, chloride's going to be -1, and then copper, again, single elements in their natural state like that are going to be 0. So then we can see some charges were changing, oxidation numbers were changing. That means electrons were being transferred. And that's, if you look up at your activity series, it's got all these E minuses all over it. That's reminding us that electrons are actually leaving those neutral atoms as they get their positive charges. And if you set up those reactions in just the right way, you can capture those electrons and make them go through wires. And that's what we do with batteries, is we manipulate these single replacement reactions and try to force those electrons in order to get from one place to another. They have to go through a circuit, and so that ends up helping us to store and use electricity in that way. All right, let's practice how to use these oxidation numbers, though. This is something to really pay attention to. If you get familiar with these rules, it's not something that's hard to do, but of all the stuff we do in Chapter 4, this is usually the thing that, like the day before the test, people want to say, can you go over that again? Didn't quite catch all those little rules, and it's because there are just a bunch of little picky rules to keep up with. Some of them you've already done before, like when you were trying to find the charge of iron in an ionic compound. Let me scroll down on this. We're going to look at the left side here. And then we're going to practice it in number 50. Together. After we practice it together, there's a quiz where you'll be able to try. You can do the quizzes as many times as you want. It's the online quizzes thing, where it's going to be questions like number 50, and I'm going to ask you to find the oxidation number of all these elements and compounds. So you'll get practice with that. And then there's a kind of group POGIL assignment I'll have you work on where you'll practice doing that even more, but we'll add chemical reactions to it as well. All right, so the first rule is one of the easiest ones to recognize over there on the left side. All right, it says elements in their elemental form have an oxidation number of 0. All right, so maybe I will zoom in on this again, and I'll just have to unfreeze it so I'm going to write it on here so you can have some examples. Let's put some examples next to these bullet points in these rules. kind of like going through the rules for sig figs or going through those solubility rules where we can just kind of apply these rules to different things. So first of all, if you have like just a piece of zinc, so maybe zinc metal, if it's just zinc, there's no charge next to it, they'll probably have solid next to it. I like to put the oxidation number just kind of up on top. I think that's how you'll do it. This worksheet has you put it down below. Maybe I'll put it down below, so that way we'll be familiar with how the worksheet will do it. I'm used to putting them up on top. It works for the diatomics as well, so if you had something like, let's just say you had chlorine gas, and it's Cl2. These are all just pure elements. I'll put that down there. All right, so any kind of just pure element, if it's a diatomic, has a little 2 after it, any other element, just by itself without a charge shown, its oxidation number is 0. So those are easy to identify. Pure elements, oxidation number of 0. All right, next one. The oxidation number of a monatomic ion is the same as its charge. All right, so an example of this could be something like Zn2+. Its oxidation number is positive 2. If it were something like Cl-, maybe it says AQ after it. Maybe it does, maybe it doesn't, but usually it would say AQ after it. All right, that oxidation number is, of course, -1. So if it clearly has a charge, we can see it from that. If it's part of a compound, maybe it was ZnCl2 as the compound, well, those would still be the ions that we're dealing with there. All right, now we get into some little more picky rules here. Nonmetals, all right, right-hand side of the periodic table, tend to have negative oxidation numbers, although some are positive in certain compounds and ions. So this is where things change up a little bit. We're used to saying chlorine is always -1 because it's in group 17. If it's a chloride ion, we said it's -1, and that's true. But sometimes in certain compounds and in some polyatomic ions, chlorine can have maybe an oxidation number of like +5. And that kind of flips things around a little bit for us. So nonmetals usually have negative oxidation numbers. They're over there on the right side of the periodic table. But some can be positive in certain compounds and ions. So here's some examples of some nonmetals to watch out for. Oxygen has an oxidation number of -2. 90% of the time or more, it's -2. That's what you would expect because it's in group 16, right? If I said, what's the charge on an oxygen in a compound? You would find O number 8, and you'd say, oh, it's in group 16. Those guys are -2. But except in peroxide ion, where it has an oxidation number of -1. So let's talk about peroxide. You're going to know that it's peroxide when it appears in very few but very specific compounds. The most common peroxide, if I just say peroxide, if I go to the grocery store and get me some peroxide, what are you probably getting? Hydrogen peroxide, right. That is, the formula is H2O2. So there's actually just some compounds to watch out for that are peroxides. In that case, oxygen's oxidation number, what we used to call charge, is actually -1, and there are 2 of them. There are also 2 hydrogens, which we know are probably +1, they are. So that's actually kind of unusual that in hydrogen peroxide, instead of being -2, the oxygen has a -1 oxidation number. And there's just a few other peroxides that exist. The other ones, it's the same pattern really. It's any group 1 element with a little 2 and then O2. So the others would be lithium peroxide is Li2O2. We've got sodium peroxide is Na2O2. So they always appear with this exact pattern. A group 1 metal, little 2, oxygen, little 2. It goes all the way down. You could do K2O2, Rb2O2. CS2O2, don't see those as often. All right, when you have a peroxide, and I say, what's oxygen's oxidation number? You're going to say it's -1. That's the only time it's going to be anything other than 0 or -2 is when it's a peroxide, it's that. If it's just pure oxygen, that gets back up to rule number 1 up top there. If it were just pure oxygen, what would the oxidation number of just pure O2 be? 0, because it's just a pure element, right? So oxygen has 3 options. It's usually -2. If it's pure oxygen, it's 0. And then if it's in that peroxide form, it's -1. Okay, I got to scroll. When I scroll, I have to unfreeze the screen. Does anybody need more time? All right, now hydrogen, we know hydrogen is almost always, think of it as +1. It's in group 1. So we looked at hydrogen peroxide a minute ago. We said hydrogen's +1. Occasionally, hydrogen can be -1 when bonded to a metal. All right, so if hydrogen's bonded to a metal, then it actually is going to be -1, and it's called hydride instead. Those also kind of look a certain weird way to us. Something like NaH, that would be sodium hydride. In that case, the sodium is +1, and the hydrogen is actually -1. We could have calcium hydride. All right, these are examples of hydrides where hydrogen is bonded to a metal. Calcium's +2 because it's in group 2. But each individual hydrogen is -1, and there's 2 of them. We can see they add up to 0. Again, compounds typically add up to 0. We're used to seeing hydrogen as +1 when bonded to a nonmetal. So those would be examples like we are used to, like H2O. All right, in H2O, hydrogen is +1, and the oxygen's -2, like it's supposed to be. So those hydrides over there on the left, those are pretty rare. Those are kind of like peroxides. You don't see those very much, but if you do see one, that's where hydrogen would not follow its usual rule from its location on the periodic table. All right, next we got a bullet point that's really easy because it's an always bullet point, and it's what we'd expect it to be. Fluorine is in group 17. These in group 17 are supposed to be -1. So unless it's pure fluorine, like F2, which is 0 if it's pure fluorine, if it's fluorine in any kind of a compound, fluorine is -1. Finally, a rule we can always follow. The reason these rules are important because these rules are going to help us find the oxidation number of other elements like iron or like lead. Like we said, you might have to figure out what it's bonded to. So if you know fluorine's always -1, that's going to be a helpful rule. The other halogens, all right, remember halogens, guys, are group 17. Those other halogens have an oxidation number of -1, like they're supposed to when they are negative. And then we get into this. They can have positive oxidation numbers, most notably in oxyanions, such as chlorate. Oxyanions are polyatomic ions that involve oxygen. So those are ones that we're really going to see some of these exceptions to our nonmetals. We're used to our nonmetals being negative, but oxyanions are those polyatomic ions that involve oxygen. Let's look at chlorate. Chlorate has a -1 charge. This will be our first one where we can really practice finding an oxidation number of chlorine. Chlorine is normally -1, but in this polyatomic ion, something else must be going on. And this is where we're really going to practice. We use what we've learned so far to figure out what the charge or oxidation number of chlorine has to be. The total charge of this whole compound has to be -1, right? Because we know chlorate, if we memorize our polyatomic ions, chlorate is -1 overall. So we're going to set an equation equal to -1, and we're going to solve it for chlorine. How many chlorine atoms are in chlorate? There's one, right? There's not a subscript after it. I'm going to say 1 times chlorine, because I don't know what chlorine is, because it can take different positive oxidation numbers. Plus, all right, how many oxygen atoms are in chlorate? 3. So I'm going to say 3 times oxygen. That's an O for oxygen, not a 0 at this point. I'll put X so we know it's oxygen. So it doesn't look like a 0. I'm going to change oxygen symbol to OX for a minute. Now, I'm going to solve this for chlorine, knowing that oxygen's charge or oxidation number is supposed to be -2 most of the time, unless it's part of peroxide. This isn't any kind of peroxide situation here. Now we're going to solve this for chlorine. That is going to be chlorine's oxidation number. All right, so when we solve this for chlorine in an equation like this, we're finding out how could these 4 atoms total come together to give us a -1 charge. So it turns out to be chlorine minus 6 equals -1. So what minus 6 is -1? Solving for x, basically. 5. You need to add 6 to both sides or just think about it that way. Chlorine's oxidation number is, and we're going to emphasize with oxidation numbers, we like to emphasize positivity or negativity. So chlorine's oxidation number here is +5. And so it's not really a charge anymore, it's actually an oxidation number. Oxidation number is like saying, if it had a charge, what would its charge have to be? So we're trying to pretend some things have a charge when they don't really have a charge. Oh, well that makes sense again. Now let's look at the formula one more time, now that we know the oxidation number. If there's 1 chlorine that's +5, learn how to write straight. +5. And then there are 3 oxygens that are -2, all coming together total. That's going to add up to -1 for the overall polyatomic ion. So again, these are really covalent bonds. The chlorine to oxygen are covalent bonds, so they're not real charges. That's why we use the word oxidation number. Oxidation number is saying, if something had a charge, what would it be? You might be thinking, why in the world do we need to know what its charge would be if it doesn't even have a charge in the first place? Because doing this, it's an accounting method that helps us follow electrons across chemical reactions to find out which atom is gaining electrons and which one's losing electrons in the course of a total chemical reaction. So this is all about kind of an accounting technique to follow the flow of electrons. And that's what they use when they make batteries to figure out what would be the best element to make this battery with. Maybe lithium would be the best element for this battery. And then how many electrons are flowing when the reaction occurs to find out if it's an efficient battery or not. Okay, and what we just did there is kind of what this next bullet point is about. The sum of oxidation numbers of a neutral compound is 0. That's what we're used to doing when we tried to find out like what's the charge of a transition metal like iron in a compound. We realized it had to add up to 0. But the sum of oxidation numbers in a polyatomic ion like chlorate, which we just looked at, is equal to the charge. That's why I set that equal to -1. So you set it equal to -1, and then you use things like oxygens or hydrogens or something like that to figure out what's the charge of, say, the chlorine or the charge of the nitrogen in nitrate. All right, let's practice with this now, and that's what we're going to do on number 4.50 there that's on the handout. It says, determine the oxidation number for the indicated element in each of the following compounds. First one, we're looking for titanium in titanium oxide there. This is what you're used to doing. This is a transition metal. You're trying to find its charge, basically. So this is what you've done before. If I want to show my work for how I'm doing this, just to get the technique down, this compound has 1 titanium plus how many oxygens are in this compound? 2. 2 oxygens. And this is a neutral compound. There's not a charge shown to it. It's not a polyatomic ion. So I need to add this together to get to 0. All right, I don't know titanium. That's what I'm looking for. But I know what oxygen is most of the time. What is oxygen's oxidation number most of the time? -2, just because of its, it's in group 16. Because of its valence electrons there, it likes to get -2. Then we solve for titanium. All right, we get +4. So titanium's oxidation number is +4. That's one. You're used to doing those. You could probably do that without writing the equation out. But that's going to be helpful for us when we looked at the next one. So now we have a system. We've got a pattern to follow. All right, letter B, we're looking for SN in the compound, or actually this is a polyatomic ion, SnCl3 negative. All right, so in this compound or polyatomic ion we're looking at, how many SNs are there? Davis, how many SNs are in SnCl3?
1.
There's just one, yeah. So 1 SN plus, how many chlorines we got here? These people are out. Alice, how many chlorines are in this? 3 chlorines. All right, and then what does this one need to add up to, Pavitra? Yeah, this needs to add up to -1 because of that little negative. It's almost hard to see there. That little minus right there. It's negative. Now, I'm looking for 10, so clearly I've got to solve for it. So I need to do my best guess on what chlorine's charge is, because chlorine is normally something. Adam, what's chlorine normally going to be for its charge or oxidation number? -1, all right? So don't let all those little exceptions we just looked at make this more complicated. For the most part, you still follow your general idea from the periodic table. There's just a few exceptions like peroxides and such to watch out for. All right, so if that has to add up to -1 overall, solve for Sn. And Sydney, what do you get when you solve that for Sn? Thank you, +2. I would have gotten that wrong. +2 is correct there. All right, so Sn, in this case, it's +2. All right, you try a couple more. You give letter C a try and see what you get for carbon. And that's another polyatomic ion there. C2O4 adds up to -2. If you're not there yet, it's fine, but MK, did you get an answer for letter C? Not yet? Okay. Kira, did you get an answer for letter C yet? You got it. So it's +3. And this is where just glancing at the periodic table wouldn't have worked for carbon, because nonmetals can actually change their oxidation numbers quite a bit depending on what they're bonded to. So 2 carbons plus 4 times -2. I know oxygen is not a peroxide here. It's not pure oxygen, so I'm going to go with the idea that oxygen is always -2 almost all the time. So we get that, and we get +3 there. They're just solving for C like you're solving for X. Yeah. Okay, let me do it step by step here. I'm going to say 2 times carbon minus 8, right, equals -2. I'm going to add 8 to both sides, step by step here. All right, then what am I going to have on the right side now, Ainsley? So I added 8 to both sides. What's left on what do I have on the right-hand side now? 6, you got it. So 2 times C equals positive 6. And so divide by 2, you get 3. So if you want to call it X as you're solving for it, that helps rather than thinking of it as carbon. And it's just the algebra part here. So if it helps to call it X, that might be helpful. While you're solving for it. And that turns out to be carbon's oxidation number in that polyatomic ion. I think it's called oxalate. So the way you could actually see that, going back to the actual chemistry, not just the algebra here, carbon 2 O4 2 minus. We've got 2 of the positive 3s. We've got 4 negative 2s from all the oxygens. Put all those numbers together, they add up to negative 2. That is the charge of the overall polyatomic ion. Let's give letter D a try. Nitrogen and N2H4. Yes. Oh, okay, thanks. Bye. Shelby, you've got a bag in the office if you want to run and get it. Take a pink hall pass. All right, now we know hydrogen's usually, what's hydrogen going to be most of the time? Piper, what would we say hydrogen is most of the time, Piper? Yeah, good. It's always almost positive 1, unless it's bonded to a metal or something or by itself. So there's 4 of those hydrogens there. So what does nitrogen have to be, Carter? Yeah. You got it. What kind of a 2? Yeah, it's actually negative 2, so this is kind of unusual. We're used to the positive going first and then the negative one coming second, but in this case, it's just the way it was written. Hydrogen's bonded to a nonmetal. We know it's positive 1, so each nitrogen must be negative 2. And in that way, all those charges, or really I should say oxidation numbers here, all these oxidation numbers add up to 0 in that way. All right, next one's good because it's got actually 3 elements to it. So give the next one a try. Let's try to find nitrogen in, it's called nitrous acid. It's a weak acid, HNO2. Kira.
How is nitrogen positive or negative in
Okay, let's go. So let's focus first on the what it's bonded to. Its partner is hydrogen, right? What do we know about hydrogen when it's bonded to nonmetals? Its charge is positive 1 when it's bonded to nonmetals. All right, so that is probably what got switched, and it's confusing for me too because I'm used to the positive one coming first in a compound. But because I know there are 4 times hydrogens, I could do the math for it. 4 times hydrogens, which I know are positive 1, plus 2 times nitrogen, which I'm looking for. This thing is a neutral compound, so it adds up to 0. I'm going to solve for N, and that's where I'll get the negative 2 there. So the order of that one, for whatever reason, that compound has its order switched, which kind of throws me off in my positives and negatives, but that's why. You're welcome. All right, HNO2, again, go by the rules that you know usually for the hydrogen and the oxygen, based on what you're used to doing with those guys, and then try to solve for nitrogen. Letter E there. let's see, letter E. Will, have you solved it for nitrogen yet? Letter E. Not yet, you're still on your way. Vivi, have you gotten into that one yet? Not yet. Have you gotten it yet, Jonathan? Letter E. It's positive 3. Yes, sir. Good job. Nitrogen is positive 3. So again, the way you'll show it on this little sheet we're about to do in a second is you'll write the oxidation numbers of everything below them. And if you have 2 oxygens, you'll put -2 under there twice. And so in that way, you'll be able to identify every individual element's oxidation numbers. And that's going to be important when you look at a chemical reaction. So you can say, oh, nitrogen on this side of the reaction is positive 3, but on that side of the reaction, maybe it's 0. So you'll actually see its oxidation number change over the course of a reaction, and that's an important thing to follow over the course of the reaction, is the change in the oxidation number from one side to the other. All right, last one is a weird one here. We got Cr2O7 adds up to 2 minus. Let's see. Davis, what did we get for chromium in letter F?
I got positive 6.
Positive 6, you got it. So that comes into some of those really, they can get up to like positive 6 or even maybe positive 7 in some weird ones. So you'll probably never see like positive 15 or anything that high, but that's one of the higher ones there, positive 6. That's called dichromate of polyatomic ion. All right. Yes. Yep. How many chromiums do I have? 2. How many oxygens do I have? 7 oxygens. What does it have to add up to? -2. Call that X for chromium. Plus, what do I know oxygen is most of the time? So you just solve it for X. Yeah, exactly. So there are probably, maybe even 1,000. There's at least hundreds of polyatomic ions. I only had you learn like 15 of them. So if it's a polyatomic ion, it will have that charge over to the upper right of it. So that is what you have to set it equal to. If it doesn't have a charge at all, it's 0, like we did in the last one there. All right. So what does this have to do with chemical reactions overall? That's what we're going to look at. We're just going to look at this first one on the bottom here because the others come from the handout that you're going to do with your group in a little bit. When you look at an overall reaction down in the lower half of this page, you want to be able to find the oxidation number for everything. In number 50, it told us, hey, focus on the chromium or focus on the nitrogen. But when you look at a reaction like this, you don't know what to focus on, so you have to give the oxidation number for every single element on each side of the reaction. When you're focusing on oxidation numbers, don't worry about coefficients. They're just to help balance the reaction overall, so you don't need to worry about those for now. Just follow your normal rules. What is the most common charge for hydrogen, or oxidation number for hydrogen, when it's bonded to a nonmetal like oxygen? Yeah, +1. So since there are 2 of them, I'm going to give hydrogen +1 for its oxidation number. What's the most common charge or oxidation number for oxygen when it's bonded to something like hydrogen? Pavitra? -2. So we're used to seeing that as -2, and that's what it is here. All right, now, remember rule number 1 for oxidation numbers? Pure elements. So Adam, on the right side of this reaction, what is hydrogen's oxidation number?
0.
It's 0 over here. I guess I could put 2 zeros because there's 2 of them, but I don't have to. And then what's oxygen's, Sydney? It's also 0. So we're just focusing on what changes, all right? Hydrogen went from +1 to 0. Oxygen went from -2 to 0. One of them always shows an increase in oxidation number, and one shows a decrease in oxidation number. All right, hydrogen's number value went down. If you're thinking about it on a number line, going from +1 to 0, it went down. We say hydrogen is reduced. This is why we get into oxidation and reduction. If the number goes down overall, it might even go from -2 to -5. It's still going down on a number line. If its oxidation number value decreases, it is reduced. If its oxidation number increases, we say it is oxidized. So overall, there's a little thing that I keep in mind that goes along with this, and it is the word oil rig. This handout that I'll give you has a different way to remember it, a different term, but I like this, oil rig. When this reaction happens, again, electrons are transferred. Oxidation, all right, oxygen in this case was oxidized, which usually the other thing gets oxidized by oxygen, but in this case, oxidation is loss of electrons. So oxygen lost electrons. That's why it went from -2 to 0, because it lost some of those negative electrons. And then reduction is gain of electrons. Thing that gets reduced oxidation is loss of electrons, reduction is gain of electrons. And that's how you can use those oxidation numbers to track the flow of electrons. Hydrogen must have gained electrons. Also, we know it went more negative. It went from +1 to 0. It must have gained a negative electron to do that. So what you're going to do for the remainder of class, first of all, there is a quizzes on Canvas that I want you to go through first. You need to do them on paper. You can use scratch paper. It's just going to ask you questions a lot like question number 50 there. So here's the compound or the polycompound. Find the oxidation number of blah, blah, blah. Just like that one. Then once you're good at that, I want you to work with your lab group. And this is one of those polar things we've seen before. And it gets into the actual chemical reactions where you can decide whether or not a element is being oxidized or reduced. It gives some examples. These always start with what's called a model. So it'll tell you to do stuff to these reactions eventually, but at first you're just going to read over these and look at these reactions, and then you'll answer the questions as you go through this. All right? So you get started on the quizzes. You will submit a screenshot of that quizzes score. posted on Canvas. So it's posted on Canvas. There's a link to it there. Maybe I can pull it up here. No, I can't scroll on there. So it's called Quizzes, Oxidation Numbers. There's the link to it. Or if you just go to the quizzes, you can use that code to get into it. Sign in with your name, and then you will take a screenshot when you get the score you want. If the first time you do it, you get a 60 and you don't want that as your score, do it again until you get a 100, and then you'll submit that. If you want some more practice on like Monday before you come back to school after the weekend, you can do it again. It's not going to hurt when you get a 90 or 80. It's not going to hurt your score if you want to do it again just to practice some more. The other thing you'll do when you finish that, you can do this independently or with your lab partner. And you're welcome. This is where you'll use oxidation numbers in chemical reactions. And if you need some help with it, just raise your hand. I'll just be walking around. I'm going to pass back a few papers that are graded as well. I've got you in your seats. Free.